Good morning, everyone. This is Mark Carkenny, the Senior Manager for Government Initiatives at ACT-IAC, and I wanted to thank you all for joining our webinar this morning. Today, we've got a very special presenter, Nicholas Spiess from Snowflake, and they're going to demo some interesting technology in the cloud smart arena. That revolves around our goal of highlighting various innovations within the President's management agenda. And this specific presentation will revolve around the IT modernization goal of the PMA. In addition, I wanted to just shed some light on an event that's going on next Thursday that's also put on by the Institute for Innovation. Igniting Innovation showcases a number of the great innovations within the government technology arena. And we are expecting a very, very substantial turnout. We've got over 200 people that had submitted their greatest innovations. We'll have 40 of them showing off their innovations in their exhibits next Thursday. And then of that, we will be crowning an overall winner. We hope that you'll be able to attend this event. As a friendly reminder, attendance is free for all federal employees, so we hope that you will come and bring your colleagues as well. And I wanted to also showcase a small visualization here that kind of shows this roadmap of webinars that we are putting on here at the Institute for Innovation with the assistance of ICF. And our first two webinars revolved around the data goal of the President's management agenda. We are now pivoting to IT modernization, and we've got some interesting potential presenters coming up in the next few weeks. So we hope that you will tune in and enjoy today's presentation and participate in any subsequent presentations. And with that, I'll turn it over to Nicholas Spiess, who is our presenter today from Snowflake. And we hope that you'll enjoy today's presentation. Thank you, Nicholas.
Hey, thank you guys very much. Hello, everyone. Thank you for your time today. And welcome to this webinar on being cloud smart and data-driven. On behalf of Snowflake, I'd like to thank all the folks at ACT-IAC and the volunteers who helped put this together. Razik, Kyle, and Mark, thank you so much. Unfortunately, I'm going to start by disappointing those guys by introducing and inducing a massive eye roll to the audience. I know it's a little bit cliche to state that the cloud is here because it's something that we in the technology world have been saying for a very long time. And actually, if I'm honest, the tech world has a habit of sort of introducing these giant buzzwords that we promise are going to change the world. It's something that we tend to do. We're still doing it. But maybe no one has gotten it worse than the cloud. I admit there may be some pretty good reasons for that. When the cloud first started and cloud service providers came online and started pushing their services, there wasn't a whole lot on the truck that made sense to enterprise organizations. That's because the cloud was really just the first iteration of itself. It was entirely infrastructure as a service. Basically, a cloud service provider would let you pick the CPU, the RAM, and the hard drive that you're going to use, and then give you a virtual machine that you could build out just like you did in your own data center. And that was kind of the problem. We already had this. At the time, infrastructure as a service wasn't truly beneficial because most of us had just deployed VMware into our enterprise, which meant for the first time, we all had an excess of compute resources in our data center that supported a ton of growth. This false start on behalf of cloud can kind of be summed up by the stigma it gained, that the cloud is just somebody else's computer. And that's my actual coffee mug. Thankfully, the education ecosystem needed exactly what the initial cloud was. I was taking classes online for my software engineering degree at Arizona State at the time, and I joined thousands of other students in computer science, software engineering, and mathematics who were developing their school projects on cheap, highly available, and usually extensively custom virtual machines. Now, other uses for the cloud existed, of course, but the mainstream first users were students. And as those students graduated and joined the workforce, or is more common these days, started a company, the demand for on-demand grew to all new heights. But things really didn't take off until the advent of orchestration tools that made auto-provisioning servers with their software already installed simple. Applications like Puppet or Chef and Kubernetes, shown by the blue box here, meant that instead of just creating blank virtual machines like in our previous slide, we could provision, power up, and configure Microsoft Windows, Windows Server, Linux, Unix, and much more that were exactly the same each time. It didn't take long for cloud providers themselves to also provide similar base machines with operating systems and licensed enterprise software pre-installed. The consistency this gave us was better for security, but really paid dividends with developers who embraced DevOps and Agile mindsets, because now they could very quickly start a development system that mimicked their production environment exactly, which is something we always needed but never really had. This platform as a service capability trickled its way up to enterprise users as well, who found the ease of setting up these boxes to be almost as glorious as ditching the need for license management, since the cloud service provider would often provide the license, including the CALs for Windows Server. You could simply select the operating system and install packages that you needed, and off you go. This new platform as a service brought with it some other benefits, too. Most notable is the widespread adoption of object storage, like S3 from Amazon Web Services or blob storage from Azure Cloud and Google Cloud Store. It's an essential part of what makes the cloud work the way that it does. You see, instead of writing files in a traditional file system like we've done for decades, object storage stores strings of ones and zeros without really concerning itself what those ones and zeros are. And once those objects are committed to storage, they can't be changed again. If you want to modify an object in an object store, you have to read out a copy of the object, make those changes, and then commit them. Metadata about the object then describes which is the newest version and which version was created by whom. This built-in versioning is the underlying capability that enables so many shared document editing functions of Google Docs and Microsoft Office 365 or SharePoint. Multiple people can edit the same document, often at the same time, without worrying about stepping on each other. Because each person's edits become new objects represented by version control and some very clever software, the various objects can be made to look like real-time editing in a group session. Auto-provisioning of elastic compute is similarly game-changing. When we had to provision each box in an infrastructure as a service setting, we didn't really get the scale that the cloud promised. But with platform as a service, we absolutely do. It's no longer odious to create 10 machines or 50 or 100. Auto-provisioning and configuration means that a massive number of compute nodes can be added to a cluster quickly without hours of build and configuration time. Combined with the unique way object storage works, we no longer need to be concerned with multiple worker processes accessing the same data simultaneously, since write contention is prevented at the storage metadata layer and not a traditional file system layer. All of which brings us to the original point of the cloud, software as a service. We're already familiar with some of these offerings. I've already mentioned a few, Google Docs, Office 365, and the like. But additional offerings are coming online all the time, and as long as they're built the right way, they can take advantage of the same architectural benefits. However, not all cloud services are native built for the cloud. Many offerings are cloud-enabled, which means they're traditional software offerings modified lightly and installed by cloud service providers to be offered as a managed service, but they're not built to take advantage of the architectural benefits of the cloud. But why should you care about that? Well, in this forum, it means that the software that we build our government on may not honestly be able to scale at the pace of the public sector. Just take a second and consider your morning commute. We've all been in the morning or even gridlock from our commute. Mine happens to be in the D.C. area, so my experience is vast and especially painful here. We all know deep down that the Department of Transportation can add more lanes, but they can't do it in real time. They're going to have to close the road and reroute traffic while they build new lanes, which makes things worse far before it gets any better. This kind of thing happens all the time in information systems that weren't built for true cloud scale. And cloud scale matters when we're trying to democratize our organization's data. In other words, it matters when we want to become data-driven. The 2019 President's Management Agenda clearly calls out the goals of IT modernization, data transparency, and a focus on people, giving folks the data that they need to do their jobs without an increase in operational burden. The PMA calls this high-value work, but the impact of people isn't just limited to government employees. In fact, the agenda talks extensively about the impact that government services has on its citizens. A 2016 American Customer Satisfaction Index gave the U.S. government a score of 68. That score, and in fact this graph, is cited by our president and his administration and shows that citizens have a difficult time working with the services that their tax dollars pay for. The administration has clearly defined their desire to become data-driven and to share that data with the citizens who are affected by it. In fact, this past January, Congress passed H.R. 1770, otherwise known as the Open Government Data Act, which explicitly communicates this purpose. So, what does it mean to be data-driven? Well, let's take a look at your friendly GPS for an example. It's relatively easy these days for your favorite router to get your current location, your desired destination, and all of the potential routes between them to pick the shortest one and get you where you need to be in the shortest distance possible. A lot of us work this way. We do what we need to do without any knowledge of outside factors that might influence the decisions we make in our day-to-day jobs. However, GPSs can now go a step further and analyze the traffic times of other drivers, looking at seconds, hours, days, and even years' worth of data, including near real time as best they can grab, in order to reroute you around congestion and get you where you need to be faster and more efficiently. The analogy of our work lives is obvious. While doing our jobs, all of us have to make decisions regardless of the suit that we wear. If you have data about the environment that you're operating in, then you can operate with those data in mind. All of our work will be faster, more efficient, and more informed. Let's take a look at an example, Cadabra.com. Well, actually, Cadabra was only considered as the name, as was Relentless.com. But eventually, the leadership of this company settled on their best choice for a name, and they chose Amazon.com. Though, funny side note, Jeff Bezos liked Relentless.com so much that it's still owned by Amazon, and if you go there, it will redirect you to Amazon. Now, Amazon started out selling books, but because of the frustration that founder Jeff Bezos felt in actual bookstores and trying to find what he really actually wanted in that store, he built a site with a very comprehensive search bar. He was, of course, very interested in helping customers find the products they were looking for, but also they were equally interested in what they wanted but Amazon didn't carry. By counting and rating the number of times that a certain book was asked for, they could gauge the demand for things that they didn't currently sell and prioritize new products. This was a total departure from how most businesses were operated. Most business owners decided to carry products based on pressure from their existing vendors or because of a move from their competition or even because of a gut feeling. Amazon carried exactly what their customers were asking for, and they asked every single customer every single time. As time went on, they also included recommendations based on purchase history of not only yourself, but of customers who bought similarly to you. They also include the ability to rate products. These ratings have become the basis of millions of dollars in buying and development decision power every single day. They're so powerful, outside companies pull them from Amazon's API so they can rewrite their product roadmaps to include features and resolve complaints they collect there. Amazon had an advantage over the rest of the industry in that they had built a unique architecture that was specifically designed to do the job of enabling its sales team, product buyers, planners, and even their partners to make better decisions with real data. But architectures and systems like Amazon are no longer one-offs with huge costs and specialized engineers. I'm going to take a few minutes to talk about Snowflake and how it's part of a new wave of technologies, built for the cloud that enable every organization to be cloud smart and data-driven. Snowflake is the very first SQL data warehouse built natively for the cloud. We were started in 2012 by data warehouse industry veterans to solve a series of well-known problems and build a sort of data warehouse that cloud-scale organizations would need. Organizations like Nike, Capital One Bank, and Epic Games, who created Fortnite, have led the charge of over 2,000 companies that are now proud customers of Snowflake. We try to take the best attributes of traditional shared disk databases as well as shared nothing databases while avoiding many of their pitfalls. All the basic elements of a traditional data warehouse were blown apart and then rebuilt, each piece with cloud technologies in mind. What we ended up with is a multi-cluster shared data warehouse. At the foundation of Snowflake is object storage, shown as the blue half circle on the slide, which allows us to store incoming data at massively parallel speeds. We're able to write that data into the immutable objects we discussed earlier, which cannot be changed and do not write block. This allows for nearly endless storage scale, which is completely decoupled from the compute that we use to target that data and respond to SQL queries. Elastic compute resources, arranged as the colorful arch in the diagram, are referred to as virtual warehouses in Snowflake, and they target the single data source of object storage in parallel, all without contention with other compute resources, regardless of the activity on the data set. Just like multiple users are able to modify objects stored Office 365 or Google Doc documents, thousands of our Snowflake virtual warehouses can target that same data set without stepping on each other. This means that unlike other data warehouses, Snowflake doesn't slow down because you're loading a large data set into it, nor does it grind to a halt when a large number of users are running queries. It also means that when you aren't using a virtual warehouse, you can simply shut it down or destroy it to save money, since you only pay for the consumption of resources, not the existence of them. And because of Snowflake's adoption of cloud technologies, it only takes seconds to provision new virtual warehouses, resize an existing warehouse instantly without downtime, or destroy resources that are no longer needed. Our shared services layer ensures that queries are compiled and executed as efficiently as possible, all the while enforcing our role-based access controls to keep data safe and out of unauthorized hands, even if you choose to share parts of that data with agencies outside your own. I built out a demo for Snowflake that only takes a few minutes and hopefully will cement the value of cloud-scale software as a service offerings and will make clear the value that the cloud will finally bring as we move to being cloud smart and data-driven. So what you see on the screen before you is the user interface for Snowflake. You're not required to use our user interface. Any open database connector or Java database connector is able to interact with our database the same as it would with an on-premise database such as Oracle or SQL Server from Microsoft. But we do provide this interface, as most software as a service offerings do, so that if you do need to interact with your data, you can. So on the interface in the top left, I have access to different objects that make up my instance, things like my databases, any shares that I've created with external customers, the compute resources called warehouses here that I use to interact with my data, and where we are now, which is the worksheets that I use to interact with the system through SQL. We're going to load some data in. This data comes from the City Bike project in New York City. This data is a bicycle sharing software that if a person in New York City wants to rent a bicycle, they can walk up with a credit card, swipe that credit card, remove the bike from the stand, write it to a delivery location, and drop it off. And that constitutes one record. But this could very easily be logistics like shipping information. It could be in the DoD, maybe personnel movements, or of course financial records. So the first thing I want to do is create a virtual warehouse. I've got 4 here, but we're going to create one dedicated just to loading because I don't want to step on any other workloads. Here, I'm going to choose the size of the warehouse, and this is One, how much I'll be charged based on performance and how many resources I consume, but also how much data I think I'm acting against. And this is only about 7 million rows, so we'll go with the extra small. Aside from this vertical scaling, I can also scale horizontally by choosing a maximum number of parallel clusters in case I had a bunch of users. As an example that we like to use is, instead of building the church for Easter Sunday, you can simply make the building as big as the people who contain in it. Our scaling policy will remain standard, and after 10 minutes of inactivity, the system will power off that asset so we don't pay for it anymore. Once we have our warehouse connected, we'll go ahead and load the data in. Now, the data that I'm loading has been staged into Amazon's S3 just to make it easy for the purpose of this demo. And once we're done loading, we'll get a record output here of all the different columns and rows of information that data contained. And it's great to look at data this way. It shows that the data is exactly what we expected and that it's there. But honestly, to take action on data, you really want some sort of visualization tool. For the sake of this exercise, I'm going to switch over to Tableau, and we can use that. And hopefully my typing skills are on point today. And it turns out they are. So this is the same data we just looked at in our browser window, but this time we're looking at it in a visual way. In the top left, this map shows all of the points of pickups for every trip that we've seen. And over on the right-hand side, it shows where all those drop-off locations were. And if we click any one of these pickup locations, the map will update automatically to show all the data relevant to that pickup location, including showing a heat map of all the drop-offs where those people went. The by week field, deselect this, the by week field will highlight traffic on the service over time. But it might be interesting to look at a different data source and understand the utilization of the service. So let's do that. Back on our main screen, I went ahead and loaded some preliminary weather data. This is stuff just from the U.S. Weather Service. And I'm going to create and run some commands that will load some weather data into our system. Now, this weather data is not structured data. This is an interesting feature of Snowflake. We can see that these files are actually JSON files, so JavaScript object notation, which is a semi-structured data type. Snowflake handles this natively. Most databases can ingest this kind of information, but it requires a transformation of that data. So a JSON file may be grabbed by your ETL tool of choice and then transformed from JSON into a structured object and then written into your traditional warehouse. The problem with that is, if that's your approach, any changes in schema, which JSON experiences fairly frequently, could end up breaking that ingest process and writing corrupt data into the database. To get around that, Snowflake uses a schema on read approach. So if we look at our data, we can see the structure of the JSON object. There's no surprises here. And by using dot notation, which we'll see in just a moment, we can access this data as though it's structured on the read side, instead of applying it on the write into the database and potentially breaking. So I'm going to load this data in, and I'm going to cheat a little bit because I'm going to alter my warehouse. Instead of having a warehouse which is a small size, I'm going to set it to extra large because this is a lot of data. This is one of the benefits of Snowflake. We can, on the fly, resize our resources to meet the demand of even the per query. Again, this is where those cloud technologies really come into play. So as the data loads, you can see we're doing a little bit of a transform here, grabbing that first column and pulling a timestamp out. This is just for convenience. We don't need to do that, but it makes the table a little bit easier for us to view later. And we can see how many records that we ran out, and it looks like about 21 million rows of weather data in about 25 seconds. So I'm going to build out the rest of this data here, and then allow us to go back into Tableau and take a look at what we're coming up with. real quick to point back at this, I mentioned we use dot notation to access the data inside of JSON objects. And you can kind of see this here. This is taking each of those important attributes from JSON and making it look like a regular table. This is a typical join with our trips table we had earlier. And it allows us to treat that data as structured, even though on disk in the database, it's still semi-structured. It's a really powerful capability that even if our schema of JSON changed later, we could still use the same mechanisms to pull that data back out. So it looks like we're all loaded. So let's go back into Tableau, and we need to choose the updated data source. So we created this trips weather view, so we'll drag over that and replace it. I'm going to jumpstart here, and we'll see that the query took a little bit longer that time because, again, we have 5 times the data going through. And if we run a query, we can see that that query response time is a little bit slower than it used to be. So let's do ourselves a favor and go to a larger warehouse. Our admin gave us a choice, several warehouses that we could use, and it's up to us as the admin which one we want to use. So we'll wake that warehouse up by setting it a query.
Nicholas, this is Kyle. We're not having a difficult time hearing you right now.
My apologies, folks. I apparently needed to dial out for a second.
Oh, no worries. We recognize we lost you, and it's good to hear that you're back. So
I am back. It feels good. Okay, so when we left off, we were looking at the large warehouse that we just got pushed over to. So now we're able to run our queries in the same performance gap that we used to have with lower data, but also a lower size. But let's take a look at this data scale. We want to see why usage changes over time. So we'll go to our by-week graph, and let's just add our temperature in average Fahrenheit to this graph. Because we have a smaller sample size, I'll go ahead and filter it so we just see that. What do you know? Nobody rides a bicycle when it's cold outside. That's essentially what we're seeing here, is that as the temperature changes, leadership and usership also changes. So let's talk a little bit more about City Bike. In this project, City Bike is funded primarily by 2 different organizations, the New York City Housing Authority and the Jersey City Housing Authority. As part of this project, we wanted to give both of those entities the ability to see the data that is directly related to their usership. So we want the New York City Housing Authority to see how many memberships they're receiving revenue from so they could better the data, which we've done. So I'm going to create a share and some data for these guys to look through. It would help if I highlighted it correctly. Two dashes for a comment. So now, as our New York City Housing Authority, you'll see the interface looks the same. And again, they could be using Tableau, similar to what we are. Any BI tool could be used, or any database query tool. So for these folks, we're going to create a share, and then we're going to use that share that was created. And we'll just go ahead and see what's out there. We can see 2 inbound shares are coming into my account as the New York City Housing Authority. And there's 2 here. One is just for administrative purposes to make the demo work. But the other one is coming from our demo account to us, and it's the City Bike database share. So let's create a database based on the share that we're getting from Demo 11, which is my main account. And we can see that we've imported close to 61 million records. Now, this is every trip that's in their database, as well as all of that weather data. And we can prove that by looking at the name of these trips. We can see that this is where all of the different groups and names come into play, including New York City Housing Authority memberships. But a problem is we see this null value. So we ask our admin to take out the null values. We don't need them there. So we'll go back over to our admin here, and we'll run a command that deletes wherever we see null. Now, this is going to take just a few seconds because we are deleting around 53 million rows. We also notice that Jersey City Housing Authority data was shown to our last view. So we don't want to let Jersey City and New York City see each other. So let's create a secure view to limit the data. What this does is create a system where we use their username and anything inside the naming block to limit who can see what. So let's go back to the New York City Housing Authority and run that same query one more time. The first thing we can see is there's now a ton less results. We only see 160,000 or just over records. And if we look for that name again, we can see that the null values no longer appear. You'll see in this column that we also only see the columns that are specified in the secure view. So payment information doesn't need to be sent to somebody who doesn't need to see that information. We can specify which columns are able to be seen when we create the share. Now, in the last part of this demo, we need to undo some serious wrongs, but first, let's do another one. If you recall, we use object storage, so even though we deleted stuff, that stuff isn't actually gone. I almost did it again with a comment. Consistency is key to success, folks. So if I use this command and I drop the table from my database, it is now gone, and we can verify that by using the select count from trips. We see that object trips does not exist. So that database is now, or that table, is now gone. Well, because of object storage and the unique way that Snowflake works, we can simply run an undrop command, and now that table is back. And this works in tables and it works in databases. But if you remember, we didn't just drop or undrop a table. We deleted a bunch of trips by killing everything that was null. You can see null is no longer here. So let's look at how we get that stuff back. First, we're going to look and set a variable. Every query that's ran in Snowflake is assigned a query ID. That query ID could be used as a point in time so that we can query what the database looked just then. We can verify that my search was successful. I looked for a delete command, and that's the ID the system assigned to that query. So if I do a count of all of my trips, I see that I have roughly 7.6 million, but our nulls are still gone. If I do a query that has a modifier to go before that query, we can see that all 61 million records are there. So we now know that we have them. So let's bring that data back. First thing we're going to do, once again, we know this is a lot of work, so we're going to make our warehouse an extra large so that we can bring this data back. Then we're going to insert into our production trip data a select statement that is all of the data minus the data that we still have, essentially grabbing both databases, old and new, doing a differential, and putting the data back. This is a critical capability, and it's enabled only through our object storage. Otherwise, the amount of storage you would consume would be exponentially large. So while this is running, and it should take about 30 seconds or so to get all of our data back, still churning away. And again, this is restoring around 53 million rows back into our database. And we can verify that now by looking at the count back to 61 million that is in our primary database. And if we look at the names again, we can see that the null value now appears with 53 million records back in it. So loading structured data, loading semi-structured data, sharing that data securely with industry and government partners, and protecting that data through time travel and continuous protection, this is what Snowflake and what the benefits of the cloud bring to IT. Now, this concludes my presentation and my demo. I can't thank you guys enough again for your participation. I'd like to reintroduce my partners at ACT-IAC for any questions they'd like me to address or any comments that they would like to make. Thanks again.
Nicholas, this is Kyle. Thank you so much. That was a very insightful presentation, and I learned quite a bit from you walking through some of those examples. What we'll do is we'll open it up to the audience for questions. We have a Q&A box that we welcome any questions from the audience. But while we wait and give folks a minute to think of any questions, I did have one for you, Nicholas, that maybe we could start with. The scalability of this is impressive, and having the object store on the back end is certainly enables and supports that. But can you give some examples of how you've been able to see this scale in the real world, and do you have any kind of real numbers or hard metrics on that?
Yeah, sure. So, we've only been around in production with production customers since 2015. We had some betas in 2014. Since then, our biggest customer right now, their total database size is actually over 40 petabytes. They have over 200,000 tables inside of that database and over 20,000 users hitting that database concurrently. Our largest table, I think, is somewhere around, at this point, 68 trillion rows of data. And I'll stress again, we go back to the cloud technology, the IT modernization. These aren't McDonald's numbers that the system is broken at. These are happy customers using the system with 68 trillion rows in a single database. So the massive scalability of this, of any cloud technology, when it's built natively for the cloud, is almost unimaginable from a couple of years ago. Great question. Thank you.
Yeah, those are impressive numbers. I don't see any questions yet, but I'll ask another one. A big part of the President's management agenda around IT modernization is, how does the federal government, address or modernize its, legacy technology? And so I think the numbers are about 80% of the federal IT budget is spent on O&M. And, these are legacy applications built in the mainframe and legacy technology. And as our customers are thinking about, modernizing, how should they be viewing Snowflake in that kind of roadmap or vision of getting off of this legacy technology?
Yeah, that's a great question as well. I think there's a couple of sides to that. The first is the personnel side, obviously. The government spends a ton of money on operations and maintenance of their systems. And I think it's not that we don't want to spend that money. It's not that we don't want to maintain systems. But if I have a talented database administrator that spends all of their days vacuuming up data that's no longer relevant to a system, or doing cleansing on that data, that's wasting that DBA's talent and time to do menial processes. It's one of the reasons Snowflake has been so successful so far. None of those things are required. Our founders had a strict vision in the places that they worked beforehand. They were told to go and create a sort of a database or a data warehouse without those tuning knobs in it that would be easier to use and require less maintenance. And honestly, to get to that point, they would have had to delete hundreds of millions of lines of code from the legacy architectures to migrate to the cloud, which is why Snowflake took from 2012 to 2015 to have real customers. We spent those years writing and completely creating a database engine from scratch to be cloud native. So as we look at how budgets are spent on operations and maintenance, for us, our approach is it's better to have those talented DBAs figure out better queries and better questions to ask to load that data in, to get more data in to a single source of truth. That's where the dollar is better spent. And I think as we see the IT modernization efforts continue to ramp up in the federal government, we'll see more efforts at not just modernizing the tools that we use, but how we use those tools. And I think applications like Snowflake are critical to those steps. Again, great question. Thank you.
Let's see if we have any questions from the audience yet. If not, I've got maybe 2 or 3 more questions, and I'll give folks some time to think of questions, and if not, go with these for now. So can you talk a little bit about FedRAMP compliance and that being a critical part of any modernization initiative around platform as a service or software as a service? Could you touch on that briefly?
Sure, absolutely. So FedRAMP is a wonderful program that helps vendors like Snowflake get their products not just in front of the federal government, but also to develop those products in a secure way that the government will feel comfortable loading their data into. There's a lot that goes into the FedRAMP project, a lot that goes into compliance with FedRAMP. Snowflake is well on the way in that journey. We're currently working with the GSA PMO to move from FedRAMP ready to FedRAMP certified, and we expect that to be done by the end of the first half of this year is our optimistic hope. But definitely Snowflake takes the security of the data that we hold very, very seriously. We're a database, right? If we leak data or if we compromise data that our customers were fortunate enough and we thank them for trusting us to hold that data, we can't betray that trust. If we do, it's the last day we'll ever be in business. So we take encryption very seriously, encryption both at rest and in flight very seriously, and the requirements of FedRAMP equally. Thanks.
Great, thank you. And maybe the last question I have is, around as we look to modernize applications, automation becomes a real important aspect of that, whether it's from continuous integration or continuous deployment of product. How does Snowflake fit into kind of a continuous integration and continuous deployment environment?
Yeah, absolutely. So one of the largest critical features of Snowflake is object storage. I go back to this over and over again, and how we've decoupled the storage from our compute side. And that's important here because we use metadata to describe what's in all of those objects in object storage. So by simply managing that in metadata, if we need to create, for example, you have a large production data set and you'd want to do some development, maybe bring in new data types like we did for the weather in the demo, or you want to bring in a new construct or a new application, instead of pointing that at the production data set and perhaps introducing some risk, we advocate very heavily for creating what we call a zero-copy clone of that production database. Since it's just metadata pointing at objects, we can fork that metadata and treat them as 2 separate databases from that moment on. That allows you to do things like rapid development or agile development while targeting full production data sets and not waiting 6 months for the production data set to duplicate, and also not introducing risk to that production data set. So as we go through rapid iterations in the federal government and we introduce more agile and more DevOps in, having things like zero-copy cloning on production data is critical to the success of that. Thanks.
Yeah, that's terrific. Well, with that, I'll turn it over to Mark. If you want to wrap us up here.
Sure, absolutely. And on behalf of ACT-IAC and the Institute for Innovation, I wanted to thank Nicholas and Snowflake for presenting today. I also wanted to thank ICF for their support in putting on this endeavor. Friendly reminder that next Thursday is Igniting Innovation, and we hope to see you all there and have your participation in that event. It's shaping up very nicely, and we hope that you will keep an eye out for future webinars, and we hope to see you on the next one. Thank you all very much.
Thanks, guys, very much.
Thank you.